रेवांत, उत्कर्ष को बोलो वापस ज्वाइन करेगा। उत्कर्ष शायद अपने आप रिमूव हो गया है मीटिंग से।
ओके मैम, उत्कर्ष त्यागी और कुमार
हाँ,
उत्कर्ष।
उत्कर्ष त्यागी, 60 रोल नंबर।
ठीक है मैम। ठीक है सर।
So in the last class, we have proved that the pressure, hydraulic pressure in the fluid mechanics is a scalar quantity. Then we have derived the equations for the hydrostatic equilibrium. Okay. So first thing in the last class, we proved that the hydraulic pressure is a scalar quantity.
सर उसे बोल दिया है।
हाँ, अगर वो ना अपने इस अकाउंट से ज्वाइन नहीं कर पाए तो जीमेल से ज्वाइन कर ले।
हाँ ठीक है सर।
है ना? Okay, so in first derivation we proved that hydraulic pressure is a scalar quantity. In the second derivation, we have derived the equation for the hydraulic equilibrium, hydrostatic equilibrium. Okay, so what was the final equation for hydrostatic equilibrium for incompressible fluids, or where when the density is constant, for incompressible fluids, when density is constant, the hydrostatic equilibrium equation is Pa by rho minus Pb by rho, where A and B are the two reference points, equal to Pa by rho minus Pb by rho, equal to G gravity constant multiplied by ZA minus ZB, difference in the elevation. Okay, so this is the equation for hydrostatic equilibrium when your fluid density is constant. Okay, so Pa is the pressure at point A, Pb is the pressure at point B, ZA is the elevation or elevation लिखो elevation of point A. ZB is the elevation of point B. Then rho is the density of fluid. So this equation is true when you have the incompressible fluid. Now hydrostatic equilibrium for the compressible fluid is represented by the barometric equation that we have also derived in the last class. So hydrostatic equilibrium for the barometric fluid. Hydrostatic equilibrium when you have the compressible fluid, है ना? For compressible fluids. So for compressible fluid, we had derived the equation that is PB divided by PA, that should be equal to exponential of in bracket minus G M capital M ZB minus ZA divided by RT. So here we assume the ideal gas law is applicable, है ना? तो यहाँ पे ये भी लिख देते हैं when ideal gas law is applicable, okay. And here so you have some new parameters. First is M. M is the molecular weight of the mixture of the component, you know, for which you are calculating the pressure, or the fluid for which you are calculating the pressure. T is the temperature, absolute temperature in Kelvin or Rankine. Okay, and R is the gas constant. Other parameters are same as we have defined in the previous equation. Okay, now this is also called the barometric equation. Now in the next topic we will study the hydrostatic equilibrium in a centrifugal field, है ना? Initially we studied the hydrostatic fluid equilibrium due to the pressure. Now we will study the hydrostatic equilibrium in a centrifugal field. Then we will go for the application of the hydrostatic equations. Okay, so the next topic is hydrostatic equilibrium in the statical fields, in the centrifugal fields. Okay, so suppose you have a vessel which is filled with the fluid, okay, given fluid, and now now you are rotating the vessel with its central axis. This is a cylindrical vessel, and now you start to rotate the vessel with the axis of the cylindrical axis, okay, central axis. So what will happen? There is a centrifugal force which exerted on the fluid. Due to that centrifugal force, the fluid starts to move towards the wall of the vessel. Okay, so I'm first I will make the diagram, then I will explain. Suppose this is a vessel which contains a fluid. This is the central axis of the vessel. Okay, now you start to rotate the vessel with angular velocity theta. So what will happen? Due to the centrifugal force on the vessel, the fluid will move toward the wall. Okay, so it will stick towards the wall and it will remain in this position. So the fluid is not flowing, है ना? It will move due to the force, then it will stay at the near to the wall, है ना? Because it cannot escape from the wall. This is the non-porous wall, okay, and it cannot also flow in any direction. So due to the force, it will remain in this condition. So what is happening? Basically, pressure force and the centrifugal force is equivalent to each other. Due to this wall, there is a pressure force in this direction and there is a centrifugal force in this direction. So both forces are equivalent. So the fluid will remain in the stationary condition. And you have to remember that we are studying the statistic fluid mechanics. So here we are studying the fluid which is present in the stationary condition, fluid which are not flowing. Okay. Now we will write the dimensions. Suppose this distance, internal dia of the this part is R, this part is R1, the total radius of the vessel is R2, and you take a small volume like control volume. We are taking in the transport phenomena. So we are taking a differential area that is from the R distance. The radius of this differential area is R and the thickness is dr. Yeah, thickness is dr. The similar way we are solving the problem in the transport phenomena. Okay, now we will make the force balance for this small area. Yeah, this is also here also. So it is a cylindrical shape area. This is also dr. Okay, so we will do the force balance for this small area, then we will integrate it for the whole system. Okay, so first I will define the parameters. So it will be, you will remember this. So R1 is the radius of the or radial distance of the free liquid surface central axis. Okay. Similarly, R2 is the radius of the centrifugal ball. Okay. Now, this fluid will work as a rigid body. This will not move. Okay. So here I will just correct it. Here we have done some mistake. This is not here. This is the R1 distance. This is R2 and R should be here. Okay, this is R and this is R. Okay. Now we have taken the small control volume inside the this structure and we will do the force balance. Okay. Now consider a small volume element of thickness R, of thickness dr, and radius r, Okay, now you have to write the centrifugal force which will work in this direction. Okay, so how much centrifugal force will be there? So centrifugal force can be calculated as dF equal to omega square multiplied by r dm divided by dm. This is the centrifugal force, not divide by. Okay, so this will be the centrifugal force. Okay, so omega is the omega is the angular velocity, r is the radius, dm is the mass of the liquid element, mass of the liquid element, and df is the centrifugal force. Okay, now suppose this is equation number 1. Now in this equation, you can represent dm in terms of density and volume. Okay. So what is the dm? Density multiplied by volume. Dm is the mass. Mass should be equal to density. Density is rho multiplied by volume. Volume, suppose volume is delta V, and delta V should be equal to for element, for cylindrical element, for the small element, delta V volume equal to, which you have already used in the transport phenomena, r 2 pi r dr. है ना, 2 pi r dr. And how it's come by pi r square, pi r plus dr square minus pi r square. That will become the pi r square plus pi dr square plus 2 pi r dr plus minus pi r square. So this will be cancelled out. This is very small quantity because dr is very small, so dr square becomes even smaller. So can be neglected. So this is only the answer. Okay, so that is the 2 pi r dr. Okay, now you can write dm equal to, does dm equal to, dm should be equal to rho multiplied by 2 pi r dr. Now substitute this value in the original equation, in equation number 1. You will get df equal to omega square r, both will remain same, and in place of dm you can write 2 pi r dr multiplied by rho. Okay, so this will be your answer. Okay, this is equal to df. Okay, now pressure force should be equal to the centrifugal force. So what is the pressure? By definition, pressure equal to, pressure should be equal to force divided by area. So because pressure force should be equal to the centrifugal force, so this value can be written or used as a as a pressure force. Okay, so what I am telling you, that because there is a force in this direction, so at the same amount of force will be at the opposite direction, so the liquid will become rigid and it will not flow. And in the centrifugal, when you apply the centrifugal force on the vessel, so the fluid will move towards the wall and it will stay with the wall. Okay, so it will be in the stationary condition. It is not moving. Fluid is not moving. Whole vessel is moving, but fluid will remain stationary in terms of the vessel wall. है ना, वैसे तो फ्लूइड मूव कर रहा है, लेकिन वेसल वॉल के रिलेटिवली वो कांस्टेंट है ना, वो मूव नहीं कर रहा है. ओके, सो इन टर्म्स ऑफ वेसल it is not moving, है ना, it will remain in the stationary condition. Okay, now pressure is force per unit area, force per area. Okay, so we can write dp equal to, force is this omega square r 2 pi r rho multiplied by dr divided by area. What is the area? Surface area. First, where the force will work? Force will work on this area. Okay, so this is like, this is basically a cylindrical area, है ना. So the perimeter of the circle is 2 pi r multiplied by length. Length is like, suppose this height is b. Suppose this height is b. So 2 pi r b, that is the surface area of the cylinder where the pressure force will apply. And it is a compressive force which will apply on the normal direction of the surface. So pressure will be applied at 2 pi. Okay, this r become Here you have 1r, here you have the double r, so I am writing the r square, है ना, तो इसको r square कर देते हैं, so it will remain easier. So this r will remove from here and it will become the r square. Okay, now here it 2 pi r, b will come. Okay, now these two r's will be cancelled out, so you will get dp equal to omega square 2 pi r rho dr. Now you can integrate from the one point to other pa to pb like the previous case. So when you integrate, then pa minus pb equal to omega square rho, and when it will integrate, it will become ra square minus rb square divided by 2. Okay, so this is the value of the pressure difference or the hydrostatic equilibrium when system is in the influence in the centrifugal force. Okay, this is when you have the centrifugal force on the system. Okay, so you have to remember this equation. This is the equation number 2. Okay, now in the next topic we will discuss about the manometers. So basically manometer is the application of hydrostatic equilibrium in the real life. So manometers are the simple device which are used to calculate the pressure difference in a flowing channel. Okay, suppose you have a flow channel, and in the flow channel what will happen, the pressure difference arises between the 2 points. If you want to calculate the pressure the difference between the 2 points, you can use the manometer. Okay, so I will show you how can we use the manometer. So there is a diagram, there is a simple design of the manometer that is called the U-tube manometers. Okay, suppose you have a 2 points. This is point A, this is PA. So basically manometers are the small tubes है ना, U type tubes. Generally, the design of the manometer is the U type. So most of the manometers are the U type. So in the U type manometers, you have the glass tube, which is in the shape of U. Okay. Here at this point you have the pressure PA. At this point you have the pressure PB. Okay. Now inside the manometer you have a fluid which is not miscible in the fluid above the in the system. And suppose this is a flowing channel. Here you have the flow channel where you are measuring the pressure difference, or this is a type of vessel. There are two different vessels. One vessel is attached here and one vessel is attached here, and you want to calculate the pressure difference in between these two vessels. So whatever of fluid filled in these two vessels, the manometer fluid should not be miscible in these two fluids, and the density of manometer fluid should be higher than the density of the fluids above the in the system. Okay, so here you have the pressure PA, here you have the pressure PB. Okay, now suppose PA is greater than PB. So what will happen? Here you have the manometer fluid which is filled inside the manometer. Generally, in general case, we use the mercury as a manometer fluid. Okay, mercury is generally used as a manometer fluid. So this is called fluid A, with density rho A. And above the manometer fluid, this is also the manometer fluid. Above the manometer fluid, you have the other fluid, which is B, and has the density rho B. This fluid has the density rho B. Okay, now we will define the different points. Suppose this is the point 1. This level is at the point 2. And if you take the horizontal line, this point is 3. And at this point, and this is the point 4, and this at the end, here you have the point 5. Okay, so you have the different points. This is point 1, this is point 2, this is point 3, this is point 4, this is point 5. Okay, now suppose the level between the two different points है ना. So here you have the fluid B with density rho B. Similarly, at this side also you have the fluid B with density rho B. Okay, now the difference between the level of the barometric fluid, the difference between the level of the barometric fluid from here to here. Suppose this difference between the point 0.3 and point 0.4, and point 0.3 is the point where which is equal to the elevation of point 0.3 is same as the elevation of the point 0.2, and the difference where the you have the where you have the fluid A, fluid B interface at this side. This is the point 2. This is the point 3, which is same elevation as the elevation of point 2. This is the fluid A, fluid B interface in the other side. So the level difference between the barometer, this is called the manometer. So the level difference between in the two different rods of the manometer is Rm. This is the difference between the rods of the two rods of the manometer. Okay. Now the height. This is these 2 points are at the same level. Point 1 and point 5 is is at the same level. So this distance is suppose Zm. This distance is Zm. So you have Zm, then Rm, then these 2 points are same. Okay. Now here you have the pressure PA, here you have the pressure PB. Okay. Now what is the, now you can write the force balance by using the by using the equations which you have studied, hydrostatic equilibrium equations, and for non-compressible fluid. Okay. So you can write PA, here you have the pressure PA. So PA is the pressure at this point, okay, plus the amount of pressure created by this distance that you can calculate it from the hydrostatic equilibrium equation which we have studied before. This equation, that is the PA minus PB equal to G multiplied by rho multiplied by height ZA minus ZB. So what is the ZA minus ZB in this point? Here the pressure is PA plus this height. This is the height Zm plus Rm. So the height is Zm plus Rm multiplied by density. Density is rho B. Okay. So that is the pressure difference between these 2 points. Okay. So now you know the pressure at the point 2. So pressure at the, because these 2 points are at the same elevation. This point and this point is the same elevation. So you should have the same pressure at this point, at the point 2 and at the point 3. And pressure should be same at a stationary condition when fluid is not flowing. Pressure should be same at point 2 and point 3. Because here you have the same fluid at the same elevation. Okay. So now you have to, because we are doing the force balance, so you have to write the pressure in the negative sign. That should be equal to, here the force at this point, here the pressure is PB, at point 5 you have the pressure PB. So PB plus pressure from point 4 to point 5, the height of fluid from point 4 to point 5, that is the Zm multiplied by multiplied by rho B. Okay. Plus this height, this is the fluid A. So this is plus, here Gc will, G also come, gravity will come, then it will become force. Okay. So here G will become okay. So the now the pressure due to the point the fluid of fluid A which has the height Rm, this height from 3 to 4 है ना, यहाँ पे जितनी हाइट है that is equal to Rm multiply by rho A multiply by G. Okay, so this is your equation number 1. Here you have done the force balance. Okay, now if you open this bracket you will find that this equation Zm will be cancelled out. So I'm just opening the bracket so you can understand what we are doing. So Pa plus Zm rho Ag plus Rm rho A, दिस इज रो ए और रो बी है ना, यहां तो आपका फ्लूइड है जेड पी ए प्लस रो बी जी and Rm plus rho Bg, that should be equal to Pv at another side plus Zm rho Bg plus Rm rho Ag. Okay, now these two terms will be cancelled out. So you will get, now I am just rearranging this equation, you will get Pa minus Pb, that should be equal to Rm will be, you can take common, Rmg will be common and it will become rho A minus rho B. So this is the equation which can be used to calculate the pressure difference between two different points by using the manometer. So this is very basic equation which can be used to calculate the pressure difference by using the YouTube manometer. So how you will calculate? Suppose your reading is, you know the elevation at this point, you know the elevation at this point, so you can calculate how much difference of this point has. Suppose this point has the 20 centimeter difference, so your Rm is 20 centimeter, gravity value you know, though you know the density of two fluids are the physical quantity which you can determine from the data books. Suppose it is a mercury, so density of mercury is 13.6 kg per meter cube, density 13,600 kg per meter cube, and density, suppose the rho b is water, so density of water is 1000 kg per meter cube. So you can easily calculate rho a minus rho b, and by using this formula you can calculate the pressure difference in between 2 points. Okay, now we will also do some experiment in the in lab class. Also we will see how can we use the YouTube manometer to calculate the pressure difference in between 2 points. Okay, I think this is enough for today's class. ठीक है?
ठीक है सर।
यस सर।
ठीक है, मैं तुम लोग के साथ शेयर कर दूंगा।
हाँ सर, और कल वाला भी वो शेयर कर दीजिएगा, रिकॉर्डिंग।
शेयर नहीं किया मैंने अभी तक।
नहीं, वो वाला नहीं हुआ है, लास्ट क्लास का नहीं हुआ है।
क्या है, मैं चेक कर लेता हूँ। कर दिया है?
हो गया सर, सारे शेयर।
हाँ हाँ,
ये सर शेयर्ड है सब,
है ना, वीडियो भी शेयर कर दी है और ये भी शेयर कर दिया है।
हाँ सर, हो गया हो गया है।
हाँ ठीक है, फिर अब मिलते हैं नेक्स्ट वीक, है ना, मंडे को तुम्हारी लैब क्लास होगी, इसमें मिलते हैं। ठीक है,
ठीक है सर।
चलो।
ओके सर, बाय सर।
चलो बाय।
चलो ठीक है, बाय सबको।